So today we are going to start with the error function. Okay, I repeat, we're going to start with the error function. Okay, so what is the error function? Okay, the error function is defined by the integral. This integral is 2 divided by root pi integration from 0 to x e to the power minus u square du. And it is represented by the error function ERF, and the argument is x. What is x here? Here x is the upper limit of the integration. Okay, this integration is called the error function. Okay, and it depends upon the value of the upper integral x. Aduga, so the factor 2 by root pi, this factor 2 by root pi causes the function to be scaled so that error infinity. Error infinity this is 2 by root pi integration from 0 to infinity e to the power minus u square du. So if this x becomes infinity, okay, so I repeat, so if this x becomes infinity, then this in the value of this integration, the net value of this integration is root pi by 2, and therefore the error function becomes 1. Okay, the value of this integration we know from gamma functions. This is equal to root pi divided by 2. So this root pi divided by 2 cancels with this 2 by root pi, and we get the value 1. So the coefficient, the factor 2 by root pi, which appears in the error function, is just a normalization constant, scaling constant. Okay. So error function this error function occurs frequently in probability, statistics, and partial differential equations. Okay. So okay. And what is the interpretation? In statistics, for non-negative values of x, this x in statistics, for non-negative values of x, the error function has the following interpretation. And what is the interpretation? That is, for a random variable y that is normally distributed with mean 0 and standard deviation 1 by root 2 pi, sorry, 1 by root 2, the error function x is the probability that y falls in the range minus x2 plus x. I repeat, you have a random variable y, and this random variable is normally distributed with mean 0 and standard deviation 1 by root 2. Then the error function x is the probability that this y falls in the range minus x2 plus x. Okay, I'll share the notes with you. And one interesting property is that the error function is an odd function. That is, if you replace x by minus x, then the function picks up a negative sign. Okay, and how do we calculate the value of this integration? We can calculate the value of this integration by using numerical methods. Okay, and what will be the graph? What will be the plot of this error function? Let us see the plot of this error function. Okay, so let me stop sharing now, and then let me start sharing the web page. Okay. Okay, so can you see the graph now? Graph record. Can you see the graph?
Ure sir.
Okay, okay. So this is the plot of the error function. Okay, so this is the plot of the error function. When x is equal to 0, the value is 0, and when x increases, the value increases in this fashion. And since it is an odd function, the the value of the integral for negative values of x is given by the mirror image of this about the origin. Okay, see. So this is the plot of the error function. So for any given value of x, you can find out the value of this integration of this function. Okay, and when x tends to infinity, this value tends to 1. Okay, so that is all about for error function today. And record. Okay, so let us look at the statistical theory of errors. So for almost all measurements, it is seen that the limiting distribution, that is the relative number of measurements for various values of errors, is a symmetrical bell-shaped curve. That is the Gaussian distribution, okay, which you are already familiar with. The mathematical function that describes this bell-shaped curve is called the normal or the Gaussian distribution. Okay, so for large measurements subject to only random errors, this measurements, it follows a normal Gaussian distribution. Okay, so let me write down the expression for the normal Gaussian distribution. So let me open a new page. Normal Gaussian distribution. Okay, so now I'm writing on a new page now. The mathematical expression is f of x. This is equal to 1 by root over twice pi times sigma exponent, that is e to the power minus, sorry, so minus, there is actually x minus lambda whole square divided by 2 sigma square. So this is the expression for the normal distribution and Gaussian distribution. Okay, and what is the plot? The plot is something like this. When I plot this, it will actually turn out to be something like this. Here, the maximum value, it occurs at lambda. Okay, and then this distribution, this value is sigma, and this value is minus sigma. Okay, so this is a normal distribution. Here, lambda is the mean, and sigma is the standard deviation. Okay, and this sigma is also called the natural width of the Gaussian function. And this can be taken as the standard error of measurement. So you must have learned in your classes on first semester that the total integration. So if I integrate this from minus infinity to plus infinity, what should I get? That is, if I integrate this f of x from minus infinity to plus infinity dx. What is the answer? This answer is actually 1. So this f of x is also called the probability density function or the probability distribution. Some probability density function. So This is the functional expression for a normal distribution. This is the plot of the normal distribution, and the total integral of this probability density function from minus infinity to plus infinity is 1. This you learned in your first semester. Now let us look at the next. What is the mean value? Oh. So what does this graph represent? The graph represents the plot of all the measurements. So here, what do we have? We have x here. And what do we have here? We have f of x here. Okay. So what have we done here? We have performed a number of repeated measurements of a quantity, and the errors present in that measurement are only random errors. That is what we are assuming. And in such a case, when we plot the values of the measurement along the x-axis and the frequency of each measurement along the y-axis, we find a bell-shaped curve. Okay, and what is the mean of this bell-shaped curve? That is, what is the mean of all these measurements? So to find the mean, that is the mean x is given by x bar. This is from minus infinity to plus infinity, x times fx dx. Okay, and this, when I substitute the value of f of x, this is nothing but 1 by root over twice pi multiplied by sigma integration from minus infinity to plus infinity x exponent of minus x minus lambda whole square divided by 2 sigma square dx. Exponent have you given? This is nothing but e to the power, have you got e to the power minus x minus lambda whole square by twice sigma square. Okay, and if we use the substitution, z equal to x minus lambda by sigma, then we can easily calculate this integral, and the value of this integral will turn out to be x bar equal to lambda y root over twice pi integration from minus infinity to infinity e to the power here it is e to the power minus z square divided by 2 dz. Okay. So after simplification, this integration reduces to this. Okay, and this will actually turn out to be, this is nothing but lambda by twice root over twice pi, and the value of this integral, as we have seen earlier, this is nothing but root over twice pi, and these two cancel out to give you lambda. Okay. So what is the mean value of x? The mean value of x is nothing but this lambda. So the order lambda is never mean values. Okay, this lambda is the mean value. Okay. So in the expression for the probability density function, here we have x minus lambda whole square by twice sigma square. This lambda is actually the mean value, and when we calculate the variance of this distribution, it will actually turn out to be sigma square. So it's written here then, and the variance, so let me write it on a new page. The variance here. Sorry, I should start a new page. So I should undo, start a new page. The variance, let us call it S square, is obtained as. So what is S square? The variance S square Let me make it full screen first. So the variance S square. The variance S square is given by integration from minus infinity to plus infinity, x minus the mean value. And we just saw that the mean value was lambda. X minus lambda whole square. This multiplied by fx dx. This will give us the variance. Okay, this integration, it will give us the variance. And if I substitute the expression for f of x, I should get root 2 pi times sigma integration from minus infinity to plus infinity x minus lambda whole square. And what is f of x? F of x, we just saw that it is equal to 1 by root 2 pi sigma multiplied by e to the power minus x minus lambda whole square divided by 2 times sigma square. So I'm integrating this with respect to x. Okay, and so if we change the variable from x to z by using the same substitution, that is z equal to x minus lambda by sigma. So if we use this substitution and perform this integration, we find that this integration actually turns out to be sigma square. So the variance of the given distribution is sigma square. Therefore, the standard deviation is sigma. Okay, the standard deviation of the distribution is sigma. So what have we seen here? We have seen here that if I have a normal distribution, so let me come back to my earlier slide. Yeah, it's here. So if I have a normal distribution here, let me also put my page, keep it like this. So if I have a normal distribution and this mean value, that is the average value, is given by this lambda, okay, and the standard deviation is given by sigma, okay. Here we can see in the expression for f of x, we can see that here x minus lambda, this lambda is the mean value of the distribution, and this sigma is actually the standard deviation of the distribution. Okay, Azuna, this is the normal distribution. Normal distribution is the lambda asina mean value ni of the distribution, sigma asina standard deviation of the distribution. So I'll pause my recording for a while.